Assalamualaikum warahmatullahi wabarakatuh, and a very good day to Dr. Roel and also Dr. Hizami. Thank you so much for your time. Okay, my name is Athina binti Wan Muhammad Rasdi, and today I'm going to present about the membrane-based venturi type microbubble generator for oxygen dissolution in water. Alright, so now this is what I'm going to present today. Okay, but the focus will be more on the results and also discussion section. Alright, now moving on to the first section, which is the background introduction. Alright, so the first one is in terms of the dissolved oxygen concentration. So DO is actually one of the most important indicators of water quality, and also it is really essential for the survival of fish and also other aquatic organisms. So when oxygen dissolves in surface water, okay, it is due to the aerating action of the wind, but also due to the byproduct of aquatic plant, namely photosynthesis. What happens is that when dissolved oxygen becomes too low, fish and also other aquatic organisms cannot survive in the system. So bacteria in the water body helps to consume the dead algae. So during this decay process, the bacteria will also consume the oxygen dissolved in the water. So this consumption of oxygen by the bacteria can actually lead to the decreased level of the dissolved oxygen concentration, and in some cases completely strip the water of all DO. Alright, and this process is actually named as eutrophication, and this decrease in dissolved oxygen concentration can cause fish kills and also death to other aquatic organisms. Alright, now moving on to the next slide. Alright, so now we're moving on, okay. Previous research has focused on treating wastewater using biological technique, which actually include both aerobic and also anaerobic system. And this method has been used widely as these techniques are actually economically low cost and produce no harm to the environment. Okay, but now we have one of the most advanced technique for oxygen dissolution in water by using microbubble generator, or known as MBG. Okay, this MBG actually has a simpler design and it offers higher capability of oxygen dissolution in the system, known as microbubbles, which have a size of about 10 to 60 micrometer are produced. Okay, so this bubble will produce through by sucking through a porous tube, in which later on I will explain deeper. Okay, so now the application of microbubble generator is that it can be used for wastewater treatment and also in aquaculture industries, such as for oyster farming. Okay, so this MBG will help in supplying dissolved oxygen concentration into the system. Alright, so now moving on to the next slide. Alright, so now moving on to the microbubbles characterization. Okay, so the first one is the high specific interfacial area. So as you can see from the figure, okay, the left one is assumed as macrobubbles and then the left one is assumed as microbubbles. Okay, so the difference is in terms of the size of the bubbles, in which for microbubbles generator, it produces a smaller size of bubbles. So when this bubble has a smaller size, the surface area actually increases, so which means more oxygen can be carried into the system. Alright, so now moving on to the second characteristic, okay, which is the long residence time. So as you can see from the figure, as the size of the bubble increases, the rising velocity of air bubbles also increases. So this is what we're trying to prevent, okay. We don't want the bubbles to have a big size because the rising velocity would actually increase, okay. So what we want is that we want a bubble with smaller size so that it can actually stay longer in the system. Okay, so now moving on to the next slide. How do we generate microbubbles? Okay, so as you can see here, when water flow rate is applied to the venturi type microbubble generator, the velocity of the water passes through the microbubble generator becomes higher compared to the initial velocity. Thus, the pressure becomes negative, okay, and air is actually being sucked automatically through the porous pipe, and also it is actually broken into microbubbles. So similarly, okay, the air flow rate and also the liquid flow rate are adjusted simultaneously through the venturi to generate microbubbles. Okay, and this concept is actually obeying the Bernoulli principle, where the pressure decreases as passing through the venturi. So some of the basic requirement that we should meet is that the P2 must be much lower compared to the P atmosphere. Alright, so now moving on to the next slide. Alright, so now the problem statement and also the hypothesis. So the first one, as you can see at the figure, okay, this is the Orifice type microbubble generator, in which we use this as a benchmark. Okay, so as you can see, the design is that air intake passes through the porous pipe, okay, by using the ceramic material or bonded net. Okay, but then this microbubble type generator have some limitations, in which number one is that thick material leads to high air resistance. Also, the high pore size and also the resistance from the wetting, all of this actually requires high power consumption. So what we have tried to make a conclusion is that a new thin material in the form of hydrophobic membrane, okay, in which in this experiment we are using PTFE membrane, okay, it actually has the potential to replace the porous pipe with low airflow resistance, smaller pore size, and also hydrophobic to offer lower energy consumption. Alright, so now moving on to the 1.3, which is the objective. Okay, so the main focus is actually to develop a membrane-based venturi type microbubble generator. So the details are as follows. Okay, number one is to investigate the effect of liquid velocity, or what we call as QL, on the rate of oxygen dissolution. And then the second one is to investigate the effect of gas velocity, QG, on the rate of oxygen dissolution, in which for both of these we will term it in terms of dissolved oxygen concentration. Okay, the third one is to investigate the combined effect of liquid and also gas velocity on the size of microbubbles. And then the fourth one is to estimate the energy consumption of oxygen dissolution using the developed microbubble generator. Okay, so what are the scope of study that we use in our experiment? Okay, number one is that we are going to vary the liquid flow rate, okay, at 10 different flow rates, which are from 35.9 to 39.6 liter per minute. Okay, and then the second one is in terms of the air flow rate, okay, 0 to 5 liter per minute. And then the material that we are going to use is the PTFE membrane. Okay, so now moving on to the next section. Okay, so this is the temperature review section. Types of microbubble generator. The first one we have the Orifice, spherical body, spiral flow, ejector type microbubble generator, pressurized, and also venturi type microbubble generator. So these all types of microbubble generator are actually using the concept of Bernoulli principle, in which when pressurized water is actually being introduced into the generator, the velocity through the tube becomes greater than the exit. Thus, the energy conservation principle, okay, it actually stated that the pressure will become negative, and also the air will be sucked automatically through the porous pipe embedded into the pipe. Okay, so and the air is actually being broken down into microbubbles. Okay, but the difference between this type of MBG and also ours is that the presence of the hydrophobic PTFE membrane that would wrap around the venturi type MBG. Okay, so next, moving on to the next slide. This is the project workflow for FYP1 and also for FYP2, the compilation. Okay, so the first one is that the preparation of lab apparatus and also experimental setup. And then we are going to test in terms of preliminary test pump calibration, oxygen dissolution performance test in terms of the DO concentration, liquid power requirement, and then the last one is the compilation of data and also data analysis. Alright, so now moving on to the experimental setup. So as you can see from the figure, this is the experimental setup that we are using for this experiment. Okay, the apparatus that we need is that 700 liter tank, submersible pump, venturi type microbubble generator, pressure gauge, F4 meter, and DO meter. Okay, so the material that we are using is the sodium sulfide with catalyst, in which the catalyst that we are using is a cobalt chloride, and also 0.45 micrometer PTFE membrane. Okay, as you can see, this is a venturi type microbubble generator, as what I've explained previously. Okay, the condition that we must meet is that P2 must be much lower to P1. Okay, as you can see from the figure. Okay, and then the velocity V2 must be much higher compared to V1 for the air to be sucked automatically and the air to be broken down into microbubbles. Okay, now moving on to the experimental procedure. Okay, so the first one is the DO reduction. Okay, so this DO reduction is really important because we want to get the correct KLA, which is the mass transfer coefficient. Okay, so that is why we need to reduce the DO to at least 0 to 0.5 milligram per liter. Okay, so first it is actually deoxygenated using cobalt chloride and also sodium sulfide in the weight ratio of 1 to 100. Okay, so to reduce about 1 milligram per liter of dissolved oxygen concentration, we need about 7.9 milligram per liter of sodium sulfide. Okay, so next is the preliminary MBG test. There are three main subtests. Okay, in which in this preliminary MBG test we are going to vary in terms of liquid flow velocity, air flow rate, and also the vacuum pressure. We are trying to find the correlation between these three. Okay. Alright, so now moving on, the first one is the oxygen dissolution performance test, in which in this test we are going to measure the dissolved oxygen increment first before we calculate the oxygen transfer rate using this equation, in which we can get the value of the KLA, which is known as the oxygen transfer rate, okay, as the slope of plotting the ln equation varying with the time versus with the time. Okay, so now the last one is the liquid power requirement, okay, in which this we will calculate using this equation, in which we are trying to calculate the pumping power using the hydrostatic pressure of water, density of water, inlet velocity, and also the liquid flow rate. Okay, so later on I will explain further in the result and discussion section. Alright, so now moving on to the result and discussion section. Okay, the first one is the correlation between vacuum pressure and also the air flow rate. Okay, as you can see, this test was actually done to study the correlation between the vacuum pressure and also the air flow rate. Okay, so what happened is that when the MBG is actually being switched on, the vacuum pressure sucks the water in the manometer to a certain height. So as you can see from the graph, as the height difference in the water manometer increases, the air flow rate increases too, as the air flow rate is actually closely related to the pressure, which causes the height difference in the water manometer. Alright, now the effect of liquid flow rate on air flow rate. So as we can see from the graph, QG increases as QL increases. Okay, this is because as the liquid discharge increases, the initial force acting on the bubble also increases. Okay, and this actually causes the bubble to have shorter attach time to the gas inlet, and this actually makes the size of the bubble becomes smaller. So and the interfacial area becomes bigger. Thus, the QG increases at higher liquid flow rate. Alright, so now move the effect of liquid flow rate on pressure. So as can be seen from the figure, the liquid flow rate actually exerted vacuum pressure. So this can actually be explained using the Bernoulli principle, as what I have explained previously, which actually explains at higher QL, the liquid velocity in the tube also becomes high. So thus the pressure drop in the venturi tube becomes high too. So this negative pressure actually causes the air to be sucked into the MBG, and microbubbles are actually being produced. Okay, so now moving on. The effect of liquid flow rate on oxygen dissolution rate. The first one is the maximum air flow rate. So this is the graph of oxygen dissolution as function of time for different liquid discharge. So as can be seen, the DO increases rapidly during the first 5 minutes. Okay, at maximum QG, the bubble characteristic changes with the liquid discharge rate. Okay, and also as can be seen, the liquid velocity below and also above 37.37 liter per minute actually shows a lower rate of dissolving oxygen, and this actually might be due to the coalescence of the bubble, which will actually reduce the mass transfer area. So thus the DO slowed down at the other liquid velocity. Okay, so now moving on to the constant air flow rate. So as compared with the maximum QG, okay, the DO increment is actually much lower. At constant QG, the increases in QL actually causes the average bubble diameter to decrease too. So this is due to the force analysis exerted on the bubble, okay, in which the surface tension actually causes the bubble produced to stick at the gas inlet. However, the QL will actually trigger the initial force to overcome the surface tension force, okay, and this will actually cause the bubble to grow bigger. However, the DO increment is low, starting at the 38.8 liter per minute, okay, and this might be due to the coalescence of bubble promoted by the too high liquid mixing velocity. Okay, so this actually causes the liquid film of the bubble to rupture when critical thickness is actually achieved, causing the DO increment to be affected. So that is why at this constant air flow rate, the DO increment is actually much slower. Okay, so now moving on. Alright, next is the effect of air flow rate on oxygen dissolution. So as you can see here, the purple line shows the optimum operating condition, as it shows the highest, which is at QG 4 liter per minute, okay, and the DO reach is almost about 9 milligram per liter. So what happens is that at higher QG, the bubble will actually grow faster, and this causes the bubble to have a bigger volume. And also, although at lower QG, it produces smaller bubble, okay, this is actually can be a disadvantageous, as coalescence of bubble might occur due to the uneven distribution of the bubble size. Alright, so now moving on to the next slide. The oxygen mass transfer coefficient. Okay, so as you can see, this oxygen mass transfer coefficient is actually being plotted, okay, by using the equation that I have mentioned previously. Okay, so the first one is the maximum air flow rate, and then the second one is the fixed air flow rate. So an obvious conclusion that we can make is that at maximum air flow rate, the mass transfer coefficient is actually much higher compared to the fixed air flow rate. Why does this happen? Okay, this is because at higher QG, more oxygen can actually be carried into the system through the bubbles. Okay, so this is why at higher air flow rate, which is at a maximum air flow rate, okay, the mass transfer coefficient becomes bigger. Also, as you can see, the trend is like the bell curve. Okay, this is the reason is because when the QL increases, the bubble diameter actually decreases. So when this happens, coalescence of bubble are highly to occur. So as what I've actually mentioned previously. Okay, so now moving on to the next slide. Alright, so now moving on to the oxygen mass transfer coefficient for the fixed liquid velocity. So similarly like previous one, okay, this KLA is actually being plotted by taking the slope of the graph. Okay, so as you can see at 4 liter per minute, it actually exhibits a high KLA value. So when this high KLA value, okay, it actually determines that the aeration efficiency also increases, because the KLA actually determines like how much oxygen is actually being transferred into the system. Alright, so now moving on to the next slide. Alright, so next is the energy consumption. So as you can see from the figure, okay, the optimum operating condition is at QL about 37.6 liter per minute. Okay, and the energy required is only 0.02 kilowatt hour to transfer 1 kilogram of oxygen. So this means that the microbubble generator is actually really effective. So the lower the energy required, the better the MBG, as it actually offers a lower energy cost. Okay, so as you can see, when QL increases, the air suck actually also increases. But unfortunately, at about 38 liter per minute, okay, it started to increase in terms of energy consumption. Why? Because when QL is too high, the bubble coalescence might also occur, which it would actually affect the mass transfer coefficient. So this is why the energy consumption actually started to rise up at about 38 liter per minute and above. Okay, so now moving on to the next. Moving on to chapter 5. Okay, so the first one is in terms of the conclusion. So what I've explained previously in the result and also discussion section, the membrane-based venturi type MBG is actually proven effective. Okay, and then the optimum operating condition is at QL 57.57 liter per minute and at air flow rate of maximum. Okay, so the lower the bubble size, the higher the interfacial area. However, if the lower the bubble size, okay, and if the distribution of the bubble size is also uneven, okay, it could actually lead to the coalescence of the bubble, okay, and this could actually reduce the oxygen mass transfer coefficient transferred to the system. So it doesn't mean that the lower the bubble size, the better the system is. Okay, so that is why we need to find the optimum operating condition. All right, so now moving on. The recommendation, okay, some of the recommendation is that we should actually apply this system to the wastewater treatment. Okay, the reason is why, because wastewater treatment could actually exhibit different results compared to just using tap water. Okay, and then the second one is by observing the size distribution of the microbubbles. Okay, for this recommendation, we could actually use a video speed test, okay, in which it would actually detect the size of the microbubbles. Okay, so this is where it is actually really important, because we could actually see whether the coalescence of bubble actually occurs or not. Okay, and then the third one is to conduct a system homogeneity test. Okay, this is also really important. Okay, because we in this research we just assume that the system is homogeneous. Okay, it's homogeneous. Okay, but then we should actually conduct a system homogeneity test, because we have to make sure that the dissolved oxygen concentration at the top, middle, and also the below of the system to be homogeneous, to be the same at all part. Okay, so that's all from me. Thank you so much. Assalamualaikum warahmatullahi wabarakatuh.